Today we're going to look at the topic of modular arithmetic. We have kind of introduction there. And well, this is something that's dealing with dividing and also look at the remainders. And we can also find this in real life sometimes, especially when you look at how we measure time. For example, if you have a certain situation where it's 10 o'clock in the morning and we're asking, well, what time will it be 5 hours from now? So 10 plus 5 is 15. So we can either say it's 15 hours, but it's also very common to say it's, well, 3 o'clock in the afternoon, it's 3 p.m. Because, well, when we measure time, we have the 12-hour system. So after 12 hours, you will just start at 1 again. So that's the idea of arithmetic modulo 12. So you look actually at the remainder when you divide by 12. So for example, if you look at 38, if you divide by 12, the remainder is 2 obviously, because, well, 36, so 3 times 12 plus 2, but that's not the only number that gives remainder 2 when divided by 12. So for example 14, we'd have to say, or 26 or 122. So we say these numbers, they are 2 modulo 12. So that's like a kind of base for this kind of arithmetic. We look at the different possible remainders. And in this introduction we look at the kind of math, the kind of arithmetic that's involved when we are talking about adding, for example, subtracting, multiplying, and even solving equations modulo. So there turn out to be a few rules there. First of all, a little notation. For example, in this situation, when we say 38 is divided by 12, remainder 2. So you could say 38 can be written as 12 times k plus 2. In this case, of course, k is 3. And that's always possible in general. When you start with a certain number n and you divide by some value d, then you can always say that the number can be written as k times d plus r. So this is the divider, this is like a factor, which of course must be an integer, and that's the remainder. So that's quite useful to remember. Let's look at an example. So we consider two numbers. We have the number x, both are divided by 12, it gives remainder 3. So divided by 12 gives remainder 3, and the number y is also divided by 12 and it gives remainder 3. And so it's also divided by 12, and we're asking what happens if you, for example, take x plus y, x minus y, x times y, and what about x divided by y? What can we say about the remainders? Well, let's first consider the situation x plus y. So can you just say that if you add up, the remainder will be 5? That's turned out to be yes, which you can easily show. For example, using that notation, we can say the x can be written as 12m plus 2, for example. The y can be written as 12n plus 3. Therefore, if you add up x plus y, it's 12m plus 2 plus 12n plus 3. And you can easily see that will be a multiple of 12, like 12m plus n plus 5. Apparently, if you add up the two numbers, then also the remainders are added. Well, the same goes for subtracting, you can easily check that. Let's also check multiplication. If you take x times y, Oh, by the way, for subtracting, maybe I should be a bit careful there, because you can say, is it possible to have remainder minus 1? Well, yes and no. Maybe normally not, but it turns out that actually it's not a problem, because if minus 1 is a remainder, then also you can add 12 to that, and then you have minus 1 plus 12 is 11. We come to that a little bit later. But it's actually also not a big problem to talk about negative remainders here. If you do the multiplication, so you would maybe expect the new remainder to be 2 times 3 is 6, and that turns out to be true. Because if you start the same way and you look at x times y, 12m plus 2 times 12n plus 3, it turns out to be a multiple of 12 plus 6. What happens? We can expand the brackets. 144m times n plus 36m plus 24n plus 2 times 3 is 6. Well, this whole part clearly is a multiple of 12. Because this is 144, 12 times 12, 12 times 3, 12 times 2. So the whole thing is a multiple of 12. So then we'll have remainder 6 if you divide by 12. What about dividing? Well, dividing is a bit more complicated. So you can actually show that it's not always going to work. For example, okay, yeah, in this example 2 and 3, it's not, you know, 2 divided by 3, it's not possible at all. So we need to adjust the example a little bit. So suppose we take x to give remainder 6. And y will give remainder 3. So what about dividing? So we take, for example, we take x to be something like 12m plus 6 and y to be 12n plus 3. And we are actually asking if you divide, will the remainder be 2? And the answer is not always. You can think of some examples where the answer is yes. So this number, how can we investigate? Well, we can try a few examples. So if x will give remainder 6 when divided by 12, so you could say the x can be 6, but also 18, 24, I make a mistake there, I think 6, 18, 30, sorry, 42, 54, etc. And here we have 3, 15, 27, 39, etc. And so we're asking if you take a number from this category divided by a number from that category, will you always get remainder 2? Well, it's very clear. Sometimes yes, you have 6 divided by 3, the remainder will be 2. Also 30 divided by 15, but for example, in this case, if you have 18 divided by 3, the remainder is 6. And there is also a more bigger one, and maybe you say, well, this one is a bit trivial, but if you just continue this sequence, there's also the number 486. And if you take 486 from this row divided by 27, you will have remainder 6 as well, and not remainder 2. So the dividing is a little bit complicated. Okay, let's see a little bit how we can deal with these kinds of rules. To summarize, what we had so far. First, the notation issue, by the way. So if you look at the number 38, if you divide by 12, the remainder is 2. So the common way to write it is the notation. You can say 38 is congruent to modulo 12 in brackets. This is you pronounce as congruence classes, and I know we also use that symbol when we have identities, but here we talk about a congruence relation. So it's congruent to modulo 12, and of course it's not then a unique value because, as you said before, also 26 is congruent to modulo 12. So let's look at a few examples, or actually a few rules. And you can find them also on page 54, key point 5.3. And it says if A is congruent B modulo M, so we're talking about modulo M there, and C is congruent D modulo M, then as we also discussed in the example, if you add up, so A plus B will be congruent, A plus C I should say, will congruent B plus D modulo M, or maybe I should do the brackets over there. And if you subtract A minus C, it will be B minus D modulo M. Multiplying A times C is B times D modulo M. And then also you can multiply with a constant. Yes. If you multiply both sides by K, yes, in this equation, then you can say that Ka is Kb, that's allowed. And it's also possible in this congruence to take the power of both sides. And that's not really strange. Not really strange if you think of taking the power, it's repeated multiplication. So that's not really a big surprise. Okay, so these are some rules. And it turns out that now it's possible to do some calculations, even without a calculator. And it turns out if you just practice that a little bit, you can easily develop some skills there. For example, suppose we would be asked to find 5 to the power 13. Modulo 7. So we'd like to find, if you take 5 to the power 13 and you divide by 7, what will be the remainder? You can say, well, I just typed on my calculator, but it turns out we can do a lot just by using some common sense and applying the rules. For example, suppose we write down some powers of 5. So we have 5, and then if you take 5 to the power 2, it's 25. And that will be 4 modulo 7, isn't it? Okay. Well, you can just simplify straight away because it's 21 plus 4. Let's multiply with 5 again. So then 5 to the power 3 will be 5 times 4, it's 20. And that's equal to minus 1 modulo 7, is it? And that helps quite a lot. It's no problem to have negative numbers. So now we are aiming to go to 5 to the power 13. So if you take both sides to the power 4, Then we have 5 to the power 12 there, and minus 1 to the power 4. It's 1. So now you can say 5 to the power 12 is congruent 1 modulo 7, and then you can just get 5 to the power 13 by multiplying by 5 once more. So 5 to the power 13 is congruent to 5 modulo 7. And well, if you're really curious, your calculator will probably confirm that. We didn't make a mistake. 5 to the power 13. It's a huge number. 1, 2, 2, 0, 7, 0, 3, 1, 2, 5. Okay, so apparently if you divide by 7, the remainder should be 5. So if I subtract 5 and I divide by 7, we should have an integer. Do you agree? Okay, let's just try. Well, that's good news. It's an integer. It turns out to be 174, 386, 160. So it turns out that so far the theory works. And you can apply these kind of rules to find the higher powers without really using a calculator. So if you practice that a little bit, you will improve your skills there. Okay, let's look into the dividing. We saw that it's a bit more complicated, and it turns out that to really solve the problem of a dividing, we'll go back to what we learned about the GCD, the greatest common divisor. So let's look at some examples first. So this is about dividing. So for example, if we have something like 15, it's congruent 3 modulo 12. That's true, isn't it? And now we may say, okay, well 15 and 3, they can both divide by 3. So is it possible to say 5 congruent 1 modulo 12? And we know that's not true. So there is a little problem there. And the problem is that in this case, that 3 and 12, so we divide by 3, but 3 and 12, they have a common factor. It turns out that the dividing is possible when the number through which we divide and the base of the modulo are relative prime. So let's do another example. Suppose we have, let's say we take 18. Okay, no. Let's look at a better example. So 24 congruent 3 modulo 7. That's true, isn't it? Because 3 times 7 is 21, plus 3 is 24. Okay, now let's divide by 3 both sides. So then we have 8 congruent 1 modulo 7. And that's true. So in this case we are dividing by 3, and we know that 3 and 7 have no common factors. They are relative prime. So the GCD is 1, the greatest common divisor. Okay, so we can turn it into a general rule. Just one moment. we can turn it into a general rule by saying if A is congruent B modulo M and D divides both A and B, so for example we had the 3, it was dividing 24 and 3, then you can do the division. Then you can say that A over B congruent B over D modulo M, but there must be this condition, only if D and GCD are relative prime, if the GCD of D and M is 1. So that's what we saw in this example. Okay, of course the next question is, what if the GCD is not 1? Well, then we have to extend the rule a little bit. So if the GCD is not 1, okay, so now we move to a general rule. So we have the same situation. We start with if A is B modulo M and we want to divide by D, but now suppose that also M can be divided by D. Yes, so D divides A, B and M, then A divided by D congruent B over D modulo M over D. Yes, and we can actually check that in our first example. So a little check. If you have 15 congruent 3 modulo 12, well the number 3 divides 15, 3 and 12. So if you divide by 3, then also the 12 must be divided by 3. So you can say therefore 5 congruent 1 modulo 4, and that's true. Yes? So it's a bit more complicated dividing, and we can even take it one step further. So it's actually very close to that rule, and this you can find it on page 57. So if the GCD is not 1, okay, we go again. So we start with A congruent B modulo M. D divides A and B. And now we have the GCD of D and M. Well, it's not necessarily 1. So then we can say that A over D congruent B over D modulo M over the GCD. Okay, you know, it looks a bit complicated, but I think if we do an example, it should be quite okay. So let's look at an example. Okay, suppose we're doing math modulo 15. And let's say we start with 96 congruent 36 modulo 15. Yes? Let's see whether I'm not lying there. Yeah, that is true, because the difference is 60, and so this is a true statement. Let's divide by 6. Well, notice that 15 cannot be divided by 6. Okay, so what can we do? 96 and 36 can be divided by 6. And then we have to look for the GCD of 6 and 15. Which turns out to be 3. That's quite easy to see. This is 3 times 2, that's 3 times 5. So then if you divide by 6, then the left-hand side will be 96 divided by 6, it's 16. Congruent 6 modulo 5. And that's true, isn't it? Yes, because they both equal to 1, congruent to 1 modulo 5. So this is a little bit how it works. So now let's see the area where this is mostly applied, and it's like solving linear congruences. And that's the main application actually, at least at this part, solving linear congruences. And that's quite interesting, solving linear congruences. Okay, so let's start with this example. We have 3x congruent 5 modulo 12. And solving, that means we want to find x congruent something, like the remainder class for x. So let's see, is it possible to divide by 3? Well, unfortunately not, because 5 divided by 3 is not an integer. So if you look at this problem, there's no solution. How do we know? Well, this is actually saying we're looking for a situation where 3x is 12k plus 5. Well, clearly the left-hand side is a multiple of 3, and this is 12k plus 5, which is, this is a multiple of 3, and 5 is not a multiple of 3, so it's impossible. So there's no solution there. Yes? Let's look at the situation where there is a solution. What about this situation? We have 3x. So this is example 1. Example 2, 3x congruent 7 modulo 11. Let's see. Definitely it's not possible to divide by 3 straight away. However, instead of writing 7, it's also possible to look at another remainder, for example 18 or 29, because if you add 11, they're the same. So you can first say we write 3x congruent 18 modulo 11. Well, 3x and 18, they can both be divided by 3. And then we have to be a bit careful. 11 cannot be divided by 3. Actually, 3 and 11, they have no common primes, so they're relatively prime. Therefore, we can just say x is congruent 6 modulo 11, and that's then the solution. Yes? Okay, so this is how you can deal with linear congruences. And I highly recommend that you just practice a few examples, and then you see that it's you can just follow some rules. Sometimes you may have to divide, so then instead of 11 you turn out with another class. Okay, maybe let's do one more together. If you have, let's do one other example. Another example. Suppose I have 12x plus 2 congruent 4x plus 7 modulo 9. So we try to find the x congruent, how much? So we try to solve this linear congruence. Well, first of all, notice that you can just subtract 4x on both sides. That's no problem. So then we end up with 8x plus 2 congruent 7 modulo 9. You can subtract 2, so we have 8x congruent 5 modulo 9. Clearly we cannot divide by, 5 cannot be divided by 8, but maybe we can find another congruence class so that it can be divided. So we have 5, we have 14, 23, 32. So 8x congruent 32 modulo 9. And so now we would like to divide by 8. We have to be a bit careful because 9 and 8, can we do that? Yes, because 9 and 8 have no common primes. So then we can say x is congruent to 4 modulo 9. And this is actually solving the linear congruence.